In the previous unit, we studied the differentiation of functions f from R to Rn. We called a function differentiable at a point C if limit x tends to c f of x minus f of c by x minus c exists. And when it exists, this limit is called the derivative of f at the point C. Recall that this is exactly analogous to what we saw for functions f from R to R. Therefore, it is natural to ask if we can mimic this definition for functions f from Rn to R. More precisely, can we say f is differentiable if limit x tends to c f of x minus f of c by x minus c exists? Please pause the video and ponder about this question before you proceed to the answer. I hope you have pondered enough so that the answer would now make much more sense to you. Notice that x and c are both elements in Rn, therefore x minus c is an element in Rn. And of course, division by an element in Rn does not make sense. One of the workarounds that we had seen before was that instead of looking at f of x minus f of c by x minus c, we could look at f of x minus f of c into 1 by x minus c. Recall that this was useful when we studied functions f from R to Rn. There, f of x minus f of c was a vector or an element in Rm, and we were scaling this vector by the number 1 by x minus c. However, even that does not make sense here because we do not know what is the meaning of 1 by x minus c. Therefore, we cannot directly mimic what we have seen so far. So the question is, what do we do now? Once again, pause the video and ponder before you proceed. And I have a small hope that at least some of you might have guessed that we can replace x minus c by norm of x minus c. This makes sense because of two reasons. First of all, norm of x minus c is a number, therefore we can divide by it. Moreover, norm of x minus c tends to 0 is equivalent to x tends to c. Therefore, we might define that f is differentiable at the point C if and only if limit x tends to c f of x minus f of c by norm of x minus c exists. And when this limit exists, we call the value as the derivative of f at the point C. Let us see if this candidate definition makes sense. Consider the function f from R2 to R defined as f of x comma y is equal to x. Intuitively, we feel that this function should be differentiable. So let us test if this is differentiable under the definition we came up with. We can see that it is not differentiable under that definition because if you consider two different sequences Sn and Tn defined as 1 by n comma 0 and minus 1 by n comma 0, then you get different values for the limit f of Sn minus f of 0 by norm of Sn minus 0 and f of Tn minus f of 0 by norm of Tn minus 0. This is because f of Sn minus f of 0 by norm of Sn minus 0 is equal to 1 always. On the other hand, f of Tn minus f of 0 by norm of Tn minus 0 is equal to minus 1. This is because norm of minus 1 by n comma 0 is the same as norm of 1 by n comma 0. They are both equal to 1 by n. Therefore, some information is lost when we took the norm of this vector. Anyway, as we get two different answers when we approach 0 along two different sequences, we can conclude that limit x tends to 0 f of x minus f of 0 by norm of x minus 0 does not exist. In other words, we can conclude that this function is not differentiable at the point 0 according to our definition. But we wanted this function to be differentiable, therefore this definition does not match our intuition. Further notice that we would want the definition to work under the special case where n is equal to 1. That means we want it to work for functions f from R to R. Once again, it's easy to see that the function f of x is equal to x is itself not differentiable under our definition. Therefore, we have to come up with a better definition, and this time we cannot blindly mimic the approach we have seen so far. Recall that a derivative is a linear approximation of a function. Therefore, given a function f from Rn to R, we are interested in a linear map L from Rn to R that approximates this function f. Further recall that an arbitrary linear function L from Rn to Rn has the form L of x1, x2, etc. up to xn is equal to a1 x1 plus a2 x2 plus etc. up to an xn. We further observed that this can be expressed as a dot product of two vectors, namely a1, a2, a3, etc. up to an and x1, x2, x3, etc. up to xn. If we want, we can express the vector a1, a2, etc. up to an as a and therefore write this as a dot x. Maybe you are more familiar with expressing linear maps using matrices, in which case you can write this as a1, a2, a3, etc. up to an multiplied with x1, x2, etc. up to xn. So these are all different ways of understanding linear maps from Rn to R. Next, we need to understand what we mean by linear approximation of f. First of all, notice that this linear approximation happens only near a point C. It is not a global approximation. So what we mean is that if you look at the difference between f of x and f of c, this behaves like a linear function. In other words, f of x minus f of c should roughly behave like L of x minus L of c. But because of linearity, we can rewrite this as L of x minus c. And by characterization of linear maps, we know we can express this as a dot x minus c. But this is still not precise. What do we mean when we say that f of x minus f of c is very close to a dot x minus c? Of course, it means that f of x minus f of c minus a dot x minus c is very small. But what is very small? How do we characterize this? That's the next question. When we studied functions from R to R, we saw that as x tends to c, this quantity converges faster to 0 than x minus c itself. However, in this case, x minus c is a vector, but the left hand side is a number. So, for this explanation to make sense, we will have to take norm of x minus c. So, what we get is that f of x minus f of c minus a dot x minus c is smaller than norm of x minus c. Or in other words, what we want is that this quantity converges to 0 faster than this quantity as x tends to c. That's what we want. More precisely, if you look at limit x tends to c of f of x minus f of c minus a dot x minus c divided by norm of x minus c, we want this quantity to be equal to 0. Notice that if this ratio tends to 0, then that means this tends to 0 faster than this. So we are exactly making this intuition precise. Let us summarize what we have seen so far by defining the differentiability of a function at a point C. Let f be a function from Rn to R and C be a point in Rn. We would say that f is differentiable at the point C in Rn if and only if we can find a point A in Rn such that limit x tends to c of f of x minus f of c minus a dot x minus c divided by norm of x minus c is equal to 0. Moreover, if such a vector A exists, then the linear map L from Rn to R defined as L of x is equal to A dot x is called the derivative of f at the point C. Notice that this definition does not help us figure out what A is. It appears to us now that we might have to guess the A. However, that is not the case, and in future videos we will look at methods to discover A. Of course, I encourage you to think about this on your own and try to come up with some conjectures. For now, let us try to see whether the function we had discussed earlier is differentiable with respect to this definition. More precisely, we are looking at the function f from R2 to R defined as f of x comma y is equal to x. As this function itself is linear, it is easy to see that this function is differentiable everywhere. More precisely, we can take our a to be equal to 1, 0. Then notice that f of x comma y minus f of c1, c2 is equal to x minus c1, which is equal to 1, 0 dot x minus c1 comma y minus c2, which is equal to 1, 0 dot x comma y minus c1 comma c2. Therefore, as f of x comma y minus f of c1 comma c2 is equal to 1, 0 dot x comma y minus c1 comma c2, the numerator in this limit is equal to 0. Therefore, we are taking the limit of 0 as x tends to c, which will be equal to 0. Thus, we have found an a as we desired, thus proving that this function is differentiable as we wanted it to be. You can similarly check that intuitively differentiable looking functions will be differentiable with respect to this definition. Of course, more on that later.